Hello chaps and chapettes. Now we're going to continue on looking at resistance today, but now we're going to actually apply some maths to it. We started a little bit before by looking at some graphs, but now I'm going to show you the equations you're going to need, which basically equates to about, 2 or 3 marks at GCSE, almost guaranteed, and also the most important experiment you will know for electricity. This experiment comes up in question form about 9 times out of 10 in GCSEs, so it's almost guaranteed 3 marks. And quite honestly, if you remember the circuit diagram for this one, you're good to go as far as electricity goes. So let's go into it right now, looking at resistance, the equations, and Ohm's law. So first of all, what thing we need to look at? We need to know what Ohm's law is, and it comes down to a simple equation, which is actually very straightforward. Because of that equation, and because of the way these things interact, we then need to look at understanding how potential difference and resistance affect the current of a circuit, basically putting a narrative behind it, a story behind it. Because it's not enough to know some maths, it's not enough to know some diagrams. In physics, there's nowhere to hide. You actually need to know the stories behind these things as well. And so if you're not very mathsy, or you think that your ability in numbers is not very high, don't worry. Physics, you still do need to know stories and you still need to know processes. So if you are really struggling with maths, you can lean on that aspect of yourself instead. So the last thing you need to be able to do is be able to design the experiments to figure out what resistance is. It's a big one. It's very important. It comes up a lot. You need to remember the circuit diagram because it's basically 2 or 3 marks guaranteed at GCSE. So let's go into it. First of all, you need to know Ohm's law, and that's relatively straightforward. What we do is we have a look at a graph, which I'll put there, hopefully in post. I'm basically waving at the air right now, but hopefully some sort of thing will magic in front of you. Basically, we need to have a graph of voltage against current. And that's going to be leading into a nice little equation for us. Now, if we plot voltage against current, we end up in an ohmic device here, not light bulbs, that gets a bit more complicated as you saw last video. Then we end up getting a straight line, okay? So that means we have 2 components. We've got voltage, we've got current, and there's a third one in there. Now, this is a video on resistance, so what do you think that third component is? Yeah, it's going to be resistance. So we can end up making an equation from this one, and it's a bit straightforward maths. I'm actually not going to show it to you right now. What you're going to do is hit the like button for me before we go to the back of the classroom, and I'm going to show it to you on my whiteboard table so that it's nice and clear what we're talking about. So hit the like button and join me in the back. Right, so we're just going to continue on looking at these graphs things here. And like I did in the previous video, we're going to have voltage on this side and current on this side. Again, independent variables should go down here really, with the dependent one up there, but this makes the maths easier, and you'll see why in a second. We're going to stick with our ohmic resistor on this one, rather than the light bulb, because, well, easier. And if we have our ohmic resistor and we increase voltage across it, we go up in a straight line. So a couple of things from this one. You should go through the origin. If you do not have any voltage, as in no potential difference, then there is no energy, and therefore there is no current, so nothing's going to move around. Duh, okay? But we do have this idea of a straight line. Now, those of you who are very good at maths, or just partially good at maths, may know this equation. This is the equation for a straight line. Y equals mx plus c, where y is going to be the y-axis, x is going to be the x-axis, c is going to be the intercept, and m is going to be something else, okay? So y, we know that's going to be our voltage, so V is equal to x. I'm actually going to put x on this side just to make it a little bit easier for me to remember. I. C, we don't actually have a y-intercept because it intercepts the origin. So basically it goes to plus 0, which means we can just effectively ignore it. And we end up with this m, okay? Now the m is the gradient of the line, okay? And that is, well, depends on the resistor. Now this is an ohmic resistor. It stays at a constant resistance. The gradient stays constant. Hopefully you are putting this together now. The gradient of this line is the resistance. So this is how you can work out the resistance by plotting voltage against current. And there you go. So R, V equals IR. That is Ohm's law, V equals IR. Now we had this with the light bulb actually. The light bulb goes up like this, and as you can see with the light bulb, the gradient gets steeper and steeper. So the gradient goes up, the resistance is going higher, and now there you go. You can see how from the last video we could tell the resistance is going higher because the more voltage we're putting across it, the more current. We didn't get as big an effect in current. So gradient was going up, resistance is going up, and there you go. Right, so let's go back to the front of the classroom and do the next step. Okay, so that's basically Ohm's law. It's a straight line equation with some other numbers, other letters on there, and it describes how voltage and current and resistance are all sort of linked and how they all affect each other. So the takeaway from this one is this. If you keep your voltage the same and you increase resistance, current is going to go down. And again, I'm not going to show this to you by waving my hands around. I'm actually going to do this on the table again. So let's go back to the back of the classroom, hit the like button on the way, and I'll see you there. All right, now I'm going to make some math teachers very annoyed because I'm going to break down algebra and just turn it into a balancing act instead of like hard and fast laws of logic. So this is the idea. We have Ohm's law represented by V equals IR. So V for voltage, I for current, R for resistance, okay? Now, we're going to keep the voltage the same, okay? Now, if the voltage stays the same, if the current goes up, then resistance must come down, provided we keep the voltage up, okay? Now, what this means is that if you have like 2 volts on one side, so like a circuit, simple circuit, 2 volts. You know, I'm not going to use a light bulb actually because that changes, so let's just take that out. What we have is a standard resistor, just a little box there, hooked up to a cell. There we go. If the resistance goes down on this thing, so we swap this out for a lower resistance resistor, then the current is going to go faster. That makes sense because we've got less of a thing blocking the current now as it goes around our circuit. So if we make this smaller, then the current is going to start whizzing around a bit faster. If we make our resistance effectively like 0, then assuming we had the same voltage, okay, can't actually do this one because then divided by 0, but there we go. But then the current would effectively go up to stupidly high rates and, you know, there we go. You'd probably end up with a fire and stuff. So there we go. Now, flip side of that though, if we increase the resistance, basically made it more difficult for the current to flow, then of course the current's going to go down, provided we keep the voltage the same. And that's the idea. If we increase or lower the resistance, our current is going to do the reverse of that, which means it goes up and down depending on the, the resistance there. Provided you keep the voltage the same. Now you could make things super complicated and then change it instead. Say you wanted to keep the resistance the same. You'd rearrange the equation like that. V over R. That's just silly. There we go. V over I. Which means that if you increase the current, provided you keep the resistance the same, then voltage should also go up. You decrease the current, voltage should also go down. So you get these interesting little... wait a second, let me just check that one. Yeah, so which means you get these interesting little interactions, okay? And there we go. This is how you can maneuver the equations around. Honestly, you don't really need to do that for most of GCSE. Most of GCSE will involve taking this equation, plugging in the numbers there or there, and rearranging to get your right answer. Okay, so that's fairly straightforward. All right, so back to the front of the classroom. Right, and that's that really. It's as simple as that. That kind of playing with equations, that sort of mathsy ability, honestly, it's getting the feel for the equation. I know it's kind of like a bit loose to talk about, but if you can look at an equation and then just sort of intuit that if you move one up, then some other part that's going to go down, then you're pretty much on your way to really getting what maths is all about, or at least in terms of the algebra applied in physics. You don't have to. I mean, you could just use a calculator and plug numbers in. But if you can do, maybe consider A-level physics or IB physics. So there you go. So what we need to do now is the most important experiment in electronics, or electricity GCSE, and that's going to be finding out the resistance of a material. And this is It's the easiest 3 marks you're going to get in GCSE. I mean, 9 times out of 10. If you don't get it in your exams, I do apologize. It's like the 1 in a million time it happens. And I know as soon as I release this video, every exam board in the entire world is going to go, well, that physics teacher there said it, so let's just remove it from the exam. Sorry. But let's go and find out how we can find the resistance of material. And join me at the back. Right, so this is the most important GCSE experiment you can do in circuitry. And it's really straightforward. You should remember it. It's going to get you those 3 more or less guaranteed marks. And for it, you need to have something to measure resistance of, some sort of power source, and 2 multimeters. One set to voltmeter mode and one set to ammeter mode. So what we're going to do is we're going to hook up our ammeter in series with our light bulb. So there's a wire there. We'll just plug that in. And there we go. And that's going to give us our current going through. And this is our voltmeter. We need to put our voltmeter around. Oh, hang on, there we go. Looking for some wires. We need to put our voltmeter around in parallel around our light bulb. Now, I'm hoping my light bulb's going to play ball on this one, because it could decide just to be very short today. Here we go. Is it working? Helps if you turn it on. There we go. All right, so we've got a negative number there, which is not super helpful, so I'm just going to switch that around. And there. All right, now, what we've done, we have got two things. Well, there's 2 ways you can do this one. One, we have got a voltage, which is given to us by 6.8, we'll just round it up there, and a current, which is equal to 1.5. Now, a small challenge on this one, you could probably tell me the resistance of this now. We plug it into Ohm's law equation, V equals IR. Not like that, because we need to rearrange it. So, there. Oh, that's so cool. Okay, no. Resistance is equal to V over I. And then 6.8 over 1.5. I don't have my calculator with me, but you can come up with that. And the units for resistance are going to be ohms. There you go. Let me know in the comment section below what that number should be. I haven't got my calculator with me. I should have brought it with me, but I didn't. So there we go. So V equals IR. Nice and straightforward. That's one way you can do it. And if you wanted to find out what the light bulb's resistance was, because it does change as we keep mentioning, you could just do that for a bunch of different points. Now, if you wanted to be better about this one, because that only gives you a small snapshot of the resistance at a single point, you could do much, much better. And that's by taking this data and putting it onto a graph. So we have I down here, V there, and you can start plotting your data. And then you end up with an idea of what the resistance does as it goes through. Now, the thing is, you won't have to do that in an exam situation unless you're doing like the practical component of your experiment. So maybe instead of doing an alternative practical paper, you are doing the actual thing, in which case, great, set that up, that's fine. What you might have to do is draw the circuit instead. So just drag you over here, okay. And the circuit looks like this. We have a power source, okay. And that's going to be hooked up to thing you are measuring. So it's thing you are measuring. And we're going to need an ammeter in there. And you're going to need a voltmeter there. Now, this is more or less guaranteed 3 marks in GCSE. Because this is the question they like to use in exams to see if you can hook up an ammeter or a voltmeter correctly. You get 1 mark for putting the ammeter there in series with your object, 1 mark for doing the voltmeter there in parallel around your object, and then 1 further mark for basically getting the circuit just correct, as in, like everything lined up and all that kind of stuff. So that's basically 3 marks in GCSE, and it comes up 9 times out of 10. I can't stress how often this thing comes up. they will often couch it in terms saying, design a circuit to measure resistance of this object, or something like that. And well, there you go, you just bash this out. You could also come across something like, say, design a parallel circuit, and well, it's got parallel circuit bits on there. Or design a series circuit, and it's got series circuit there. This is a really, really, really important circuit. If there's nothing else you remember from this video, this is the thing you should remember. Go away, draw it now. Pause the video, draw it now. In fact, pause the video, hit the like button, draw it now. And I'll see you at the front. All right, so there we go, guys, and that's basically it for a wrap. I didn't mention a challenge for today, but that's because I'd like for you to come up with your own challenge. I'm just going to see if that works there. So write down in the comments section below, what do you think is a worthwhile challenge for today's video? Off the top of my head, I think I can't think of anything, actually. I mean, I've been blasting out challenges for videos for most of the videos on here, but I actually can't think of one. So let me know what you come up with in the comment section below. But what you should know from this video is you should know what Ohm's law is. And that's going to be the simple equation V equals IR. Okay, if you want a way of remembering it, VIR. Okay, VIR. You should also understand how potential difference and how current and how resistance are all linked and what happens there when you start increasing the current, when you start increasing the voltage, all that kind of stuff, keeping one thing the same. You should then also be able to do that really, really important diagram, and I'm really hoping that you've actually done the sketch right now. Go away, sketch it out 3 times, 4 times, it's guaranteed 3 or 4 marks. Unless the exam boards catch wind of this video and decide to remove it from the exams from now on forever. But if they do, well, I guess you won't have to remember it, so there you go. All right, guys, that's it. Remember to hit the like button on the way out, and if you haven't subscribed already, please do subscribe. I post videos quite regularly. All right, guys, I'll see you in the next video. Have a good one.